Hello folks, and welcome back on this quite frankly beautiful spring day. Now, as much as I would like to spend the time walking around in the sun like everybody else, I've got a lot of work to do for Computex getting this G-Skill build done, plus a load of other customer stuff, so I think it makes sense instead to go into the workshop and we can do a little bit of machining. I wanted to talk today about how to machine the distro plates themselves. So that means turning it from a big slab of acrylic like one of these into something a little bit more refined like one of these. Now, I'm going to go over the steps on how to do this, along with a lot of the other things that you should be considering along the way. Now, I just want to urge, this is not the only way to do this. This is a very much a custom field, and everyone has their own different methods. I'm going to be showing the ones that work very well for the stuff that I do. They might be different to some of the other ones that you're going to see online. There are lots of people who make really fantastic distro plates out there, and everyone has their own little twist on things. This is how I do it, so this is how I'm going to work. To demonstrate it, we're going to be making the counterpart to this rather large distro plate. Now, this one's going into a build that a friend of mine is doing for Computex 2019 as well, and it's pretty huge. So this thing is about 670 millimeters tall, and there are going to be two of them. So we're going to be going over the process of how to take that 10 millimeter frosted acrylic that I just showed you and turning it into this counterpart. For making the distro plates themselves, I like to focus on 5 key points. The first one being your CAD, the design you're working towards. The second one being your tooling, what tools do you have at your disposal and how should you use them. The third one being your work holding, that's important for different parts that might need to be repeatable or flipped. And the fourth one, your CAM, how is your machine going to be run and how you're going to approach your cutting strategy. The fifth one is the actual machining itself, and that will include checking things like your material tolerances and making sure that everything is running as it should be. Now, it's important to recognize that a lot of these points sort of overlap one another and they can all affect each other in different sort of ways. For instance, the work holding and the tooling can vastly affect your model because you might not be capable of doing particular actions, say if a drill bit or an end mill is too short. Alternatively, if you need to flip a part and there's no reference surface or way of doing that, then you're going to have to think about changing the model, perhaps to have points that can be recognized in both operations. Now, we've already largely covered the CAD section of that in our previous videos showing you how to design a distro plate in Fusion 360, as well as how to integrate a pump into a distro plate in Fusion 360. If you haven't seen those videos, I 100% recommend having a look through them. If you have and you're just here for the machining parts itself, brilliant. Let's jump into the tooling. It goes without saying that your tooling is going to greatly affect not only what you can get out of your machine, but how you're going to be approaching a given cutting job. You need to tailor your tooling depending on your materials, your type of machine, and also how you intend to use them. If, like me, you have a CNC router, there's a good chance you have quite a high RPM spindle as well, so maybe rocking between 18,000 and 30,000 RPM. The thing is, at these speeds, you're best off using this sort of end mill for most of your jobs, which is a single flute. The handy thing about a single flute end mill is that it's really good for chip evacuation, and that's one of the most important things to consider when you're machining. Thinking about chip evacuation is vitally important. You need to make sure that those chips get out of the cut itself, otherwise you risk recutting them, which can have all sorts of terrible consequences. If you're cutting aluminium and you recut the chips, you stand a good chance of gumming up the actual end mill itself. It won't be able to cut properly, and it's either going to snap or it's going to push against your part, ruin it, mar it. You won't get any proper finishes, and you're probably going to destroy your tool as well. If you're cutting acrylic and it doesn't evacuate, then it's a very similar story. It's just going to melt around the end mill itself, and it'll be like glue. It will stick to it and stop it from cutting any further, and very easily chip these kind of end mills because they have quite sharp ends to them, and that will make it absolutely useless for future jobs. If you're just starting out, I 100% recommend getting some sort of cooling system just to be able to spray, if anything, cold air over the part as you're cutting it, just to get the chips out. And even with acrylic, which you can cut dry, you're best off using a minimal coolant system, maybe with oil or maybe even just the air itself. Quite often I only need to use the air. If I'm using a larger tool, I'll probably just use a little bit of oil just because I get a better finish that way. In terms of which cutters to look for, that's a little bit trickier because it's very much location dependent. Sadly, if you're stateside, I can't really help you very much there because I don't know a whole lot about their tooling, just because most of them tend to sell only locally. And if I tried to import them, they'd either be in imperial sizes, so I'd have to adjust a lot of things on my end, or they'll just be very expensive due to tax and all that. I'm better off buying from within the EU instead. If you happen to be EU based, my personal favorites are made by Datron. They get a really good mix of both being decent value, they're not insanely expensive, but also they're very high quality and they are designed specifically for these applications. Datron machines are very high RPM spindles and they're primarily used for cutting aluminium and plastics. Well, that's exactly what we're cutting here, so it sort of makes sense that they would work out pretty well. For finishing passes, I'm a huge fan of the polished cut end mills because they leave such a clear cut. It can almost look like a complete window if you get your settings right. For roughing work, I tend to use the 4-in-1 end mills just because they work fantastically well in both acrylic and in aluminium. So it means I can have one set of end mills and it will work fine for both. On that note, if you do plan on doing both acrylic and aluminium, I would recommend making sure that your end mills are kept separate for those. The aluminium ones will wear out faster than the acrylic, so I wouldn't want to use those too much on the acrylic ones just because you won't get as clean a cut at the end of it if they've been used a fair bit. Now, whilst I love these Datron ones, I wouldn't recommend getting stuck in straight at the beginning with them just because they are more expensive and you're going to be having to learn how to use things, so you're more likely going to be breaking things at that point. After that, it's just general carelessness. I still break things from time to time, it's just what happens, I'm afraid. So these ones I use quite frequently from Sorotec in Germany, and they're really fantastic value. They're 1/8 inch size. They also have little carbide drills, which I find very effective for doing the holes in the distro plates. And the good thing about these is if you break one or two, you can actually buy them in sort of 5-packs for the same price as one of these end mills. You'll get more longevity and a better finish out of the better end mills, but for the money, these are pretty fantastic. When starting out, I'd say it's a good idea just to check through and get a few different types just so you can get comfortable with things and know what works out for you and the sort of jobs you're going to be using. Now, if you want to get a little bit more exotic, I really like thread mills. The thing about making distro plates is that there are hundreds of holes at times. If you've got quite a large plate, you can have anywhere between 50 and 150 holes. And quite frankly, the prospect of doing all those by hand or even with a power drill is just, it's horrible. I've done it before and I never want to do it again. It's much easier to do it all on the machine if you're able to. So the way that I do it is I use either a thread mill cutter, which cuts all the way in and does the thread at the same time, or for the larger diameter ones, I try to use a thread mill like this. So I'll be boring down with one of the standard 4-in-1 end mills, and then I'll go over it in a second pass with a thread mill so that I can have a thread of my choosing. Now, the great thing about this is that thread milling allows you to adjust the size of the thread very minutely, so you can adjust exactly how tight your fit is going to be. Now, a lot of the time this isn't maybe that important, but if you have a time where you need to have a very, very tight friction fit or something that's just a little bit looser for maybe whatever reason you may have, you can have that control and it's quite really convenient. The other thing is it doesn't actually take very long. So if you're doing 200 holes, I found it can save a massive amount of time, and that time can be spent doing other parts of the distro plate. Typically, I tend to use the 5 and 6mm cutters the most, followed by the 8mm ones, and then the smaller ones, maybe the 2 and 3mm cutters, a little bit lower than that, and then there's the more speciality ones. The reason for that is that I get a lot more cutting rigidity from the larger tools than I do the smaller ones, so I get better finishes, but I don't want to go too large because my machine isn't all that powerful, so I'd rather stay well within its power limits to get a good cut so I'm not choking down the machine. Workholding is one of those things that's both incredibly important, but also quite machine and job specific, so you need to be quite flexible in the way that you approach it. My personal favourite method for most of the plates that I do is I use these little steel clamps combined with 3M double-sided tape. Now, I'm not kidding, this stuff is absolutely amazing, especially if you have a fixture plate like my one. Now, it does also work fine on MDF as well, but it will strip out and it won't have the same kind of repeatability as you would on a plastic plate or a metal plate. But I do find it works really, really well. Now, the way that I'll use these two is I'll take some of the double-sided tape and put it on the back of the acrylic. Then I'll place it onto the bed itself in the desired location. Then I will tighten it down with these particular clamps, like so. The double-sided tape has an interesting role to play in all of this, because whilst these provide plenty of clamping force to stop it from moving anywhere, the issue with clamping down on anything is that sometimes you risk kind of bowing the center up if you're not completely straight. Things like that can cause issues. And the double-sided tape, the handy thing is if you put it sort of evenly across the surface, it will help prevent the material from bowing as you're cutting it. Now, don't rely on all of that to do the work. You have to be careful and actually check and make sure that your material is flat enough to begin with, but it does definitely help. The other handy thing is that most of the time we're doing slotting type cuts, which are going to take one part out of a much larger sheet. So that does mean you've got to think about how your part is going to be held onto the plate when you've cut through it. So the first thing you should really try to do is be as accurate as you can. If you get it just right and you've got a nice flat bed to your machine, you actually can just machine down to the layer of plastic which will hold it down. The issue there is sometimes if your plastic itself waves around, you'll cut through it. You can't really do anything about that, that's not your fault. And other times you might get it just slightly wrong and then it's going to be too much. Where this comes in handy is that by putting this underneath, it doesn't really matter if you cut through the entire layer, maybe into your baseboard a little bit, just because this tape will keep it in place and stop it from getting flung across the bed when it has its final cuts. Toolpathing is one of those areas that can be quite difficult to get into when you're starting out, largely because there's an awful lot of information out there, but not necessarily all of it is applicable to your given situation. It's one of those things that it changes a lot depending on your materials and your machine. What works for one person may simply just not work for another. So what instead I'm going to be doing here is going over the way that I do it, and I would recommend simply experimenting and seeing what works for you. It's better to play it safe at first and see how it goes than go too hard, otherwise you risk just breaking things and you'll just waste a lot more time. I would also make sure to set up some test pieces rather than launching straight into something finished, because there's every chance that something might go wrong, or you might be able to learn a better method in the meantime which will work better for your final piece that you want to cut. So looking at this one, the first thing to take note of is our setup. So if we go take a look at it, what I've done here is I've gone into stock and I've set the width to be 350mm and our depth to be 750mm. Now this is the size of the piece of acrylic that I'm going to be using as my stock. If we go into the setup, we take a look at the origin. I've selected this point up here to act as our 0 point. Now the good thing about this one is that because it's on the corner and by the edge, it's going to be quite easy to locate it in the middle of the acrylic, because I want to make sure that there aren't going to be any clashes. So I haven't modelled them in here, you can do, but we're going to have clamps up on the top here and down at the bottom. So I want to make sure that all the toolpaths are going to be as far away from that as possible. Showing the size of the stock here makes that much easier, although you don't actually have to do it. If you're working with a very large piece, it might be quite cumbersome, so instead you can just work with your origin point and do it all on the machine instead. The next step that I like to move on to are doing the holes. So I've got the pump bracket holes here, and the majority of the holes going in for the distro plate itself. Now the reason I like to do the holes first is because sometimes if things go wrong, say with your material, you can figure it out quite early on with these parts and actually salvage it later. Now I had one batch of material that came as extruded acrylic rather than cast acrylic. Now the issue with this is you have to use different strategies for it, and because I started with the drilling, I was actually able to salvage the whole thing because it started melting it quite early on, so I could work out what the material was and how best to tackle it. For the drilling toolpathing itself, I'm using a deep drilling strategy which can be found under the Cycles tab, although I don't actually need to do this. I'm mostly using it because I find that my post processor doesn't seem to work well with the regular drilling and chip breaking commands, so deep drilling it is. The handy thing about deep drilling is it fully retracts the tool, so any chips that are maybe inside the flutes do get blown out. I'm using a pecking depth of only 4mm just to make that a little bit easier. Most of my drills are quite small, so it's a bit easier to make sure that none of the chips are going to clog and you'll get a better, cleaner cut. The next part we're going to be taking a look at are these LED grooves that run along the sides here. And to do this, I'm going to use a 5mm 4-in-1 end mill. The easiest way I find is just to use the 2D contour and select one of these contours on the inside. Under the Passes tab, I'm going to go with a multiple depths and of only 2mm roughing step down. Now I can't go much deeper than this, but I find this is a really good way for doing it very quickly and for getting a great chip evacuation and a surface finish. So what I'm going to do is just go with the 2mm multiple depths, and I'm also going to click both ways. So this will greatly reduce the cycle time because this is a very long part, and I don't want to have the tool go all the way to the top and then have to come all the way back and then do it again, when it's much easier if it just goes up and then back down and back up again. If we look down here, I've also left a stock to leave. This is because we're going to be doing a finishing pass along the edges. We don't need to do one on the base just because it's a frosted material, so it's going to look exactly the same, but I've left it at 0.1mm for that. We then finish with a finish pass, which just covers all of them at once and only takes 0.1mm off the edge. The next thing to tackle are these G1/4 inch ports. And the way I'm going to do that is with a bore command using the same 5mm tool. Now, because these are 11.8mm in diameter, it does mean that I'm going to have to do a couple passes, because obviously if you tried boring down around the outside of an 11.8mm hole with a 5mm end mill, you're going to be left with a little bit on the middle. Now that is probably fine, but I'd rather avoid it because sometimes it can flick it out and be a bit nasty. So I'd rather just cut it out properly instead. We just simply go into the passes tab, and you'll notice that I've clicked multiple passes and I've put a step over of 1.5mm. It's important though, under heights, I've selected the top height to be stock top rather than the hole top. Now the reason for this is if we take a look at these holes over here, these are actually inset quite a bit below the surface of the stock. And because we haven't milled out this pocket yet, that means that to get to that hole, it would have to plunge straight through the material. By setting it to stock top, it's going to have a spiral which goes all the way from the top to the bottom, and it won't have any issues. With the ports now done, it's time to work on the bigger cuts, and we're going to be starting with this little channel at the top here. Now I've used a 2D pocket for this, but it's better to demonstrate it on the large one here. So the reason I've chosen a 2D pocket over something like 2D adaptive is because if we take a look at this thing, up here you see there's a very tight neck. Now on an adaptive strategy, it would go all the way across, like left to right here, like so. Now that would be fine for all these large sections, but as soon as it gets to these small ones, it would then tighten up and it would go like dat, 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 really, really quickly. And I'm a little bit worried about doing that at a high feed rate because my machine isn't that rigid, so I'd rather work within the confines of that. Now you may have noticed that I seem to have a sketch here, and this is because if we take a look over here, this port is exactly the same size as the channel. Now of course if you try and 2D pocket this, it will come up with boundary points like here, such as on this circle, or in other points, and it will try and machine down into parts you've already worked with. To get around this, I just make a new sketch and project the geometry, and then I select this contour instead. What I've done is under the geometry, I've selected this chain, and that selects the whole thing. And you don't have to worry about any of the ports or any of the other work, it will just do it automatically to that depth. In terms of feeds and speeds, I'm going with 20k RPM and a 314 meter per minute sort of surface speed. So that translates to a 1300 millimeters per minute cutting feed rate. And I'm going to be having a stock to leave of 0.2 millimeters on both axes. We now want to move on to the finishing strategies. So for mine, I'm going to be using a horizontal toolpath. Now this one works very well for flat surfaces, I find, and it can give you a really nice smooth finish. You can also change the step over if you're using larger or smaller tools, just to be able to make sure that you have exactly the right finish that you want. You'll notice what I've done is I've taken the cutting feed rate and I've moved it down to 800 millimeters per minute instead, just to make it a little bit slower, more controlled. And then under passes, we've still got stock to leave, but instead what I've done is I've taken the axial to 0 and I've left it on the radial instead. The finishing pass for the exterior of the channel, we're going to be using a 2D contour with a 0.1mm axial stock to leave. Now the point of this is we don't want to have a witness mark as the tool goes around the outside, round the outside, round the outside. So to get around that, all you need to do is raise it by 0.1mm, which will be all but invisible when you take a look at the actual plate, and that gets rid of the witness mark and leaves you a lovely fresh cut and ensures that the tool isn't going to be cutting on more than one surface at any given moment. This next step is a very important one, but also nice and simple. We're going to be doing the O-ring groove, and for that I'm going to use a 2mm end mill. All you need to do is use a 2D contour, and I like to work from the outside in. So I've selected the outside contour here, and you'll notice that this doesn't look like it's 1.3mm deep. And you'd be right, this is only 0.5mm. And the reason for that is I want to have full control later on the machine to be able to change things depending on the material tolerances. In terms of feeds and speeds, it's nice and simple, 20k RPM, 800mm per minute. I'm using a ramp to get it into the actual channel itself. 10 degrees works quite nicely. I find 2 degrees just makes it a lot longer for no real reason. You can plunge cut fine, but I don't want any marks. Since this is a 2.2mm O-ring groove, obviously if we're using a 2mm tool it won't be wide enough, so we then do the interior afterwards. Finally, with all the main features cut, we can move back to the 5mm single flute end mill and then do the rough cuts of both the right and the left, which again are being done with a 2mm step down, multiple depths, and a stock to leave of 0.2mm and this time 1mm axial. Now the reason for the large axial stock to leave is I'd rather do multiple cuts just to be able to get a really good surface finish than do one really thick one. And you'll see what I'm going to be doing with that in a second. Switching over to the exterior finish pass here, you'll see that what I've done is I've kept the same axial stock to leave, 1mm, and this time I've removed the radial. So this means the end mill is going to be using the majority of its length to cut a nice clean pass around the outside here, and this should leave a really mirrored finish. On top of that, we then add another pass, this time reducing the axial to 0.4mm. Now I do this mostly just to prevent any kind of movement of the plate. The acrylic is getting quite thin now, and if you go too far at any given point and you break through, then you want to make sure that the cutting forces are minimal, otherwise things can move, you can chip the edges, and you can mar the part. We then finish up with another 2D contour, which is the exterior depth cut. Now what this does is it has no stock to leave at all, and it just cuts straight to the bottom. I always leave this one to the end, and I usually put it on an extra tool actually, just so that I don't have it happen by accident. I tend to leave my feed rate fairly conservative at only 800mm per minute. That way it's not going to be exerting too much force at any given moment, and the part should stay nice and held firm to the base. Right, it's finally time for the actual machining. So starting off, what we're going to be using is a 3.5mm microcarbide drill, and that's going to be drilling the 3.5mm holes that we're going to be tapping later for the pump bracket. Moving on, next one's going to be one of these, which is a 4.1mm carbide drill, and this is going to be doing the majority of the holes that are going to be holding the whole plate together. So these are quite important, and I really like these particular drills because they've got quite a long flute length, so I can use them for a lot of different materials. We're going to be doing the majority of the pocket cuts using one of these, which is a 5mm 4-in-1 end mill. Now what's special about this one is that I've chosen a very short flute length. Now I wanted to try and keep the flute length as short as possible because that's going to increase the tool rigidity and it means I can choke up on the tool a little bit more. The 22mm ones are great if you're doing the thicker ones, but we're only working with 10mm acrylic here, so it makes sense to use something like a 13mm like I'm doing here. Finally, the last tool that's going to be used is the 2mm polished edge end mill, and this one's going to be used for the O-ring grooves. Now I'm going to be covering that in a little bit when we've done the first bits of the machining, because there are some extra steps that I would definitely recommend taking if you're cutting an O-ring groove. We're now at a really crucial part of the plate because we're going to be making the O-ring groove. Now, I may have mentioned before, but acrylic, when it comes cast, is simply not flat. And actually, the thicker the acrylic gets, the more wacky the tolerances can become. Now, 10mm tends to work pretty well, but it still varies by perhaps even up to 0.5mm across a large sheet. Now, this is quite a large sheet, so we're going to have to play it very, very safe with this one. And the way that I like to do that is I like to machine only 0.5mm down to begin with as a single pass. Then I take a pair of calipers and then measure the depth of the groove around different points of the plate. Now, once you've worked out how deep it is in general, you can sort of take an average of that and then add that value to your Z height, and then you can machine it again to the full depth. Now, the good thing about this method is that it allows you to have a little bit more control, and just in case the material is really wacky, you can still correct it. The only issue is that it doesn't really give you the level of control you need if you've got a really, really out of spec material. But if your material's that far out, then I would suggest giving it a good proper facing job. Then you can make it really flat and work at it from there. And that's the way you do it if you're doing, say, something with acetal. I would always just face that, just because it usually comes in a variety of different thicknesses. So for acrylic, because you want the maximum optical clarity, it's better to avoid trying to do that. But if you need to, say if you're working with really thick material, I would definitely do that. Well folks, I hope you found that interesting and helpful. I'm really happy with how this plate came out. I think the frosted effect works really well with the shape of this particular reservoir. I've now got to go make the O-rings and then seal it all up with all the screws and whatnot before sending it off to Mike so that he can put it into his build for G-Skill. Speaking of which, I've got to get back to my own G-Skill build, so I guess I'll catch you in part 2 for that. And just so you don't miss it, make sure to subscribe to the channel. Also, you can check us out on Facebook, Instagram, builds.gg and Discord. I'll catch you later.